Last time we were talking about carbonyl reactivity. We went through the pi star. Yeah?
For the study guide, do you want us to do our work on the study guide, or can I do it in a notebook?
You can do your notebook. You can do your work in a notebook, on a computer, however you want. That's fine. You won't ever even turn it in. All you're going to do is click on Learning Suite that you did it, and I will give you credit for it. Now, that means you can game the system and pretend like you did it and say you did, but the joke's on you because 85% of your score is not on saying that you did it, but actually getting the benefit of having done it, right? So, okay, good. Well, we were talking about carbonyl reactivity. We had talked about the pi star, how it's mostly on the carbonyl carbon, and that's why the carbonyl carbon is electrophilic. And then we had learned to start ranking carbonyl compounds in terms of their electrophilicity by looking at what this Y group is that's connected to the carbonyl carbon. And we went through an extended discussion about whether or not that Y group is a good leaving group versus a poor leaving group, and whether it's a good electron donor versus a poor electron donor. Happily enough, those are almost the same thing, just in reverse. Yes?
Y is the same thing as Z in the book, right? They use Z in the book, is that right?
Yes, Y is the same thing as Z in the book, I guess, only Z is less patriotic because we're at BYU, right? So, I don't know. Sorry about that. So, notice that the best leaving groups are also the poorest electron donors, and the poorest leaving groups in general, with some exceptions that I'll talk about later today, are the best electron donors. And for the same reason. What makes something a good electron donor? It has a pair of high energy electrons that are unstable and that it's willing to share. What makes something a good leaving group? It has a low energy pair of electrons that it doesn't need to share because they're perfectly stable. This is going to rely on a lot of stuff you learned in 351 about pKa, and remember that good leaving groups are conjugate bases of strong acids. Why are they strong? Because the thing that's left behind after the proton gets removed is perfectly stable on its own, okay? So good leaving groups, poor leaving groups, we're using that to rank carbonyl compounds. We did that for, say, the ester and the acid chloride, recognizing that the Y group, once it had left, is methoxy for the ester or perhaps some other alkoxide, whereas for the acid chloride, it's Cl-. Cl- is an excellent leaving group. It's the conjugate base of a strong acid, HCl. It's perfectly stable on its own. For the same reasons, it's a poor electron donor. So you would predict that the acid chloride would have a more electrophilic carbonyl carbon, a more electron poor carbonyl carbon than the ester, where the leaving group, the Y group, is a methoxy group. Conjugate acid is an alcohol, pKa around 16, not particularly acidic, meaning methoxy is pretty reactive. It's a good electron donor, and so you would predict that the carbonyl carbon of the ester would be less electrophilic. What we're talking about for that methoxy being an electron donor is this arrow that I drew in this resonance structure last time. The group adjacent to the carbonyl carbon, if it has a lone pair of electrons on it, and if it's a good electron donor, can do this arrow, sharing those electrons with the carbonyl carbon. That spreads out the positive charge on the carbonyl carbon, making the carbonyl carbon less electrophilic. We could draw similar resonance structures for the acid chloride. It's just that this arrow wouldn't mean as much because the chloro is not as good of an electron donor. Okay? Questions about that? All right, so let's practice a little bit with some example carbonyl compounds. And all I want you to do is rank them in terms of electrophilicity at the carbonyl carbon. So here is another example of the ester. We get tired of methoxy. Let's use ethyl. So this is an ethyl ester. ET is the abbreviation for ethyl, just to get you. That's added. The 9 o'clock kids didn't learn that, so you are now at an advantage because you know what ET means. Versus this molecule, which is an amide. So those are the two leaving groups. Draw them as they would be with their negative charge after they had left. Get a sense for which is the best leaving group. To do this, you can look it up in a pKa table in chapter 2 or at the end of your textbook or at the end of the exam. Conjugate acid of the ethoxide group is ethanol, which has a pKa of 16. In contrast, the conjugate acid of NH2 minus is NH3, which, if you look that up, that has a pKa of 38. So that's orders of magnitude worse of a leaving group than the ethoxide group. That means it is also a better electron donor, meaning you would expect the amide to be less electrophilic at the carbonyl carbon. Okay? And it had better be, because if you know a little bit about biology, you know that the workhorses of biochemistry, the things that do the chemistry, the structural proteins, the things that make your muscles work, are all polyamides. Proteins are polyamides, lots of amide bonds. There's a reason why they're not polyesters, and that is because polyamides are less electrophilic, less reactive, more stable than are polyesters. That's also why your guts need such acidic conditions to hydrolyze proteins so that you can digest them. That's also why you have enzymes like trypsin and chymotrypsin to accelerate the hydrolysis of amide bonds. Okay, so amides are more stable than esters. Amides are less reactive than esters is the same thing as saying NH2 minus is a worse leaving group than OET minus. Okay, got it? Let's do another one, perhaps less familiar. Let's do, yeah, that's fine. Let's do ester versus thioester. What is a thioester? A thioester is the version of ester where the oxygen from the OR group is a sulfur instead of an oxygen. Sulfur's from the same row of the periodic, same column of the periodic table as oxygen, one row down. Again, we don't need to repeat this stuff about what the leaving group is for the ester. For the thioester, the leaving group is RS minus. That's called a thiolate. That's the sulfur version of the alkoxide leaving group that we've got up here. Thiolates have conjugate acids that are called thiols, and if you look those up, those have a pKa of around 8. So compare that to 16, and you tell me who is more electrophilic at the carbonyl carbon, ester versus thioester. Thioester, great. So you would predict that thioesters are more electrophilic at the carbonyl carbon than are esters. Now, while we're at it, tell me about thioester versus acid chloride. Which is more electrophilic at the carbonyl carbon? Thioester or acid chloride? Acid chloride. Better leaving group, poorer electron donor. You got it? So actually, when you deal with carbonyl compounds, that's why it's not, you can take the approach of, okay, I'm going to memorize everything that happens to an aldehyde, then I'm going to memorize everything that happens to an acid chloride, then I'm going to memorize everything that has to do with an ester. If you see them all as versions of the same thing and can rank them in reactivity, the stuff we're going to talk about is going to make so much more sense. Also, it's interesting to note that biology doesn't use acid chlorides to do chemistry, in part because they're too reactive, they're not very stable in water. There are things that they can do in water. For reasons you have just explained, thioesters are less reactive than acid chlorides, but are more reactive than esters, and so biology uses thioesters. They're electrophilic enough to do interesting chemistry, but they're stable enough not to do things that biology doesn't want to have happen. We'll see thioester-based chemistry a ton in chapter 7 when we get to metabolism. Okay, one thing we need to talk about, though, as I alluded to earlier, is aldehydes and ketones. These are kind of weird. for reasons that will become clear in a second. Every time we've looked at a molecule so far where we saw that the Y group was a cruddy leaving group, it was also, the fact that it was a cruddy leaving group meant that it was an electron, a good electron donor. And in part, that was because all the Y groups that we've dealt with so far have had lone pairs on them that could potentially be electron donors. Aldehydes and ketones are a little bit different because the Y group lacks lone pairs. So here's an aldehyde and here's a methyl ketone. In an aldehyde, the Y group would be H minus. That is a terrible leaving group. You can tell that's the case because the conjugate acid is hydrogen, which has a pKa of 35. You can look that up. I just happen to know it because I've taught the class for probably more than half the time you've been alive. So it just gets in there and whatever. Now, normally you would think that something that's a terrible leaving group might be an awesome electron donor, but hydrogen is not an electron donor. Why? There are no lone pairs or even any bonds that hydrogen's bonded to that might possibly donate electron density. The only electrons that hydrogen has are the electrons in that CH bond, okay? So even though H minus is a terrible leaving group, aldehydes are still very electrophilic at the carbonyl carbon. Okay, so I told you before, in general, if you've got a poor leaving group, it's a good electron donor. This is the one case where that's not true. Why is it not a good electron donor? It simply doesn't have lone pairs. Yes? Oh, sorry. Faked you out. Excellent. All right. So let's now talk about ketones. So for ketones, the Y group is, say, CH3 minus, which is also a terrible, horrible, very bad, no good, no, I got that wrong, no good, very bad leaving group. You can tell that's the case because its conjugate acid is methane, which has a pKa of 50, meaning never in the history of the universe has water stolen a proton from methane. That's what that pKa number sort of tells you. So CH3 minus is a terrible leaving group. Now, it also lacks lone pairs, but it has something that the hydrogen of the aldehyde doesn't. It has CH bonds. It has bonds between the atom here, the carbon, and then other things. So there are electrons there, but they're not lone pairs, they're involved in bonds. So we need to ask the question, is the alkyl group, what is the impact of the alkyl group on the electrophilicity of the carbonyl carbon? One way of asking that question is to ask, is the alkyl group an electron donor? That question is complicated and it's somewhat controversial. There's a simple answer to it and a more complicated answer to it. The simple answer has the advantage of being easy to remember, but the disadvantage of being possibly wrong. And that is that as people do more high-level quantum mechanical calculations, they're seeing that the simple explanation that's given in textbooks about alkyl groups and whether they're electron donors may not be precisely 100% accurate. Humans generally will choose simplicity anyway instead of 100% accuracy, so I'm going to tell you the simple method and you're welcome to remember it, but I'm also going to tell you the more complicated explanation as well, at a level that I hope we'll be able to deal with and understand and which will continue to be useful to us. I just don't want you in the future when you're scrolling, because I know your Google News feed is full of chemistry, but at some point if you see a headline from Nature that says, alkyl groups are not actually electron donors, I don't want you to have a, curse you, Dr. Price, moment as you think about what I told you that wasn't 100% accurate. So, first, there's one way of understanding that the impact of the alkyl group on carbonyl-carbon electrophilicity, and that is something that's called an inductive effect. So to understand this, the argument goes, and you may have heard this before, if you think about, we'll just draw the resonance structure of the carbonyl carbon that has, of a ketone that has a positive charge on the carbonyl carbon. The argument goes that sp2 carbons are more electronegative than sp3 carbons because of their increased S character. Atoms that are sp2 hybridized are 33% S. That means their orbitals penetrate to the nucleus more. The closer the orbital is to the nucleus, the lower in energy it is. And so you can think of sp2 carbons as being more electronegative than sp3 carbons, or so the argument goes. If that were true, then you would predict some kind of bond dipole that would allow, just through the sigma bonds, the electrons in this carbon-carbon sigma bond to lean a little bit into the carbonyl carbon and mitigate that positive or diminish that positive charge on the carbonyl carbon. And that's an effect that's less than what's going on for that difference in electronegativity is bigger than what's going on for the difference between carbon and the aldehyde hydrogen. So that's one argument, that through differences in electronegativity, the alkyl carbon can donate electron density through the sigma bond into the carbonyl carbon. Or in other words, electrons in this CC bond lean a little bit towards the carbonyl carbon, which decreases the positive charge and makes the carbonyl carbon less electrophilic. That's the simple argument. Go ahead.
So you see if I'm understanding correctly, that central carbon there is mostly or slightly sp2, but kind of sp3?
No, the central carbon there is absolutely sp2. Yep. Yeah, I mean, if we draw the resonance structure for the ketone, the other resonance structure for the ketone, it becomes clear that that one's, yeah, sp2. Yep, good. Others? Yeah.
And because it's sp2, because sp2 is a little more electronegative than sp3, that's why we have that inductive.
That's right. Yep, that's why we have that inductive effect. Now, that's the one that some people are saying is wrong or over exaggerated, but it has the advantage of being simple because you're used to thinking about electronegativity. Here's the more complicated one. Prepare yourself. So, this is the more complicated explanation, which is probably more true, is the one that's called hyperconjugation. It's like conjugation, only hyper. No, really it is, hyperconjugation is something new that you may have heard about before, depending on when and from whom you took 351. We're going to keep it pretty simple. Hyperconjugation is an effect where a filled orbital can donate electron density I'm going to add an adjective or adverb there, partially donates electron density into an empty orbital. And I'm going to add the word adjacent to an empty adjacent orbital. Hyperconjugation is where a filled orbital in an organic molecule, usually a bonding orbital or perhaps a lone pair, donates electron density into an adjacent empty orbital. And that's usually the empty orbital is some kind of anti-bonding orbital. Overall, the effect is stabilizing because if it allows the electrons in the filled orbital to be not completely but partially delocalized. And electron delocalization is always stabilizing. It allows the electrons in the filled orbital to move to a slightly lower energy level. Okay, so hyperconjugation is where a filled orbital overlaps with an empty orbital and donates electron density partially into the empty orbital. Hyperconjugation can happen when the filled orbital is adjacent to the empty orbital and when the two are lined up side by side. Okay, yeah?
No, you said it goes into an antibonding orbital. Wouldn't that cause instability in the other?
Right, so I'll show you an example of this, but that is why the question is, wouldn't donating electron density completely to an antibonding orbital break a bond? Yes, that's why I said partially. It's not fully sharing the electrons, it's somewhat partially sharing electrons with it. Yes?
In this example, is it the MTP orbital on the carbon?
Is it the MTP orbital on the carbon? Close, it's the pi star. Yeah, so I'll show you an example of this in the carbonyl compound. So let's draw, we're going to take the overhead view of a carbonyl compound. Here is the adjacent CH bond. We'll call this the alpha carbon because it's adjacent to the carbonyl carbon. From this perspective, I'm going to draw the carbon-oxygen pi star, which we did last time. I told you that it's mostly on the carbonyl carbon, somewhat on the carbonyl oxygen, and then below the plane of the page, you've got the other side of the orbital, which you can't really see and which has opposite wave function sign from what's on top. That's the empty, oops, wanted the pen. That is the empty carbon-oxygen pi star. And that's our view looking down on the molecule from above. Now, on the adjacent alpha carbon, we've got 3 CH bonds, and depending on rotation around that carbon-carbon bond, one or more of them could be lined up with the pi star. Let's show you we'll worry about just one of them for now. What we're going to draw now is going to rely on some 3D visualization, so we'll try to do this and then maybe we'll draw it from another perspective, see if we can help you out a little bit. You have to imagine this carbon-hydrogen bond coming out towards you sort of at an angle. Now I'm going to draw the filled carbon-hydrogen sigma bonding orbital. What does a carbon-hydrogen sigma bonding orbital look like? It looks like you had an sp3 orbital on this alpha carbon that overlaps with a 1s orbital on the hydrogen to make a large lobe of electron density here, and then there's the other side of the sp2 or sp3 orbital on that carbon. We'll choose orange here and pink here. You have to imagine that CH jutting out towards you at an angle in a way that it would line up with this orange part of the pi star. Okay? And just to highlight it, there are 2 electrons, they're in this bond, in the CH bond. Now, if that view is a little bit difficult, we're going to do the Newman projection. I often can't resist this, so this is evil Sith Anakin saying, "I hate you" to Obi-Wan. And that's how you're feeling about me right about now. We're going to look in the plane of the page at the carbonyl carbon. So here is that carbonyl carbon. We're going to do sort of a Newman projection, so the carbonyl oxygen's behind us and we can't see it. Here is the R group to our left. Here is the alpha carbon to our right. The hydrogen in question is coming out in this direction. I'll just abbreviate the other 2 like that. The pi star that we can see on the carbonyl carbon looks like this. And then the portion of, and then the sigma bonding orbital on that alpha carbon, that sigma CH bonding orbital looks like this. And you can see from this perspective that they are indeed lined up with each other. Okay, when this happens, the electrons in that filled bonding orbital can delocalize a little bit, not completely, into the carbon-oxygen pi star. So I'm going to use dotted lines to indicate partial delocalization. Why do I say partial? If it was complete, you'd expect 2 things to happen. You'd expect 3 things to happen. If it were complete, if these electrons delocalized completely, the hydrogen wouldn't be held onto anymore. there'd be a pi bond between these two carbons, and the carbon-oxygen pi bond would have broken. That's not happening here. What's happening is partial delocalization. So the electrons in this CH bond are leaning a little bit towards the carbonyl carbon. There's a lot of leaning going on in this class. So leaning a little bit towards the carbonyl carbon. That's what hyperconjugation is. And it has the effect, two things. First, the electrons in this CH bond are going to move a little bit lower in energy because they're spread out more, and delocalization is always stabilizing. Second, because they're leaning towards the carbonyl carbon, hyperconjugation is going to make the carbonyl carbon less electrophilic. Okay? So, whether or not you view the alkyl group as a donor via an inductive effect or via hyperconjugation, the overall impact is the same, which is the carbonyl carbon is less electrophilic. Now, one interesting preview is if the electrons in that CH bond from the alpha carbon are delocalized a little bit into towards the carbonyl carbon, you would predict that this hydrogen wouldn't be held onto as tightly. What holds that hydrogen there are these electrons, and if they're spreading out a little bit, you might expect that hydrogen to not be held as tightly. And that's actually true. This proton that's alpha to the carbonyl is more acidic than you would expect for a regular CH bond. We're going to use that like crazy in our preparation for exam 2. Okay? Questions about that? So overall, you predict the ketone is going to be less electrophilic, still electrophilic, but a little bit less electrophilic than the aldehyde. All right, questions about that? Yes?
So that would mean that it's less reactive for a nucleophile. Could we also say that there's steric hindrance going on?
Yeah, so the question is, you'd say that the aldehyde, the ketone is less electrophilic than the aldehyde. What role does steric hindrance play? That's a great question. Often in organic chemistry, there are two things going on at once. What I just told you about electron donation, that's what we call an electronic effect, anything involving sharing of electron density. What you just asked about, which is sterics, that's related to how big something is, and repulsion as large groups in molecules tend to approach each other. Sterics versus electronics, yeah. You might predict that a nucleophile would bump into this methyl group more than it would bump into the hydrogen, and that's generally true too. So in this is a case where both steric arguments and electronic arguments tell you the same thing, that the ketone should be less electrophilic than the aldehyde. To what extent is it sterics versus electronics? I don't know. I think probably the electronic issue is a bigger one. Other questions? Yeah.
Is it okay to think of hyperconjugation as like a pseudo-orbital resonance?
Yes, that's why it's there. The question is, can you think of hyperconjugation as sort of pseudo-orbital resonance? Yes, in fact, that's why it's called hyperconjugation. Yep, other hand. Yeah.
So, just a little confused. So if the CH bond is lower in energy, then technically it would be stronger, right?
Yeah, so the question is, if the CH bond is lower in energy, would it be stronger? Well, what we're doing with hyperconjugation is we're taking a step away from the idea that the only way to think about electrons is two electrons in a bond shared between two atoms. Here we're allowing two electrons to be spread out over more than two atoms a little bit, and that has consequences. That makes the molecule more stable overall. From the perspective of those two electrons, they are lower in energy. Two things are happening at once. The fact that these electrons are moving over makes the carbonyl carbon less electrophilic, but that alpha hydrogen correspondingly more acidic. Yep. Yes?
Why would it partially fill the empty pi star instead of the empty p orbital?
Why would it partially fill the empty pi star versus the empty p orbital? Actually, I think the question I think is related to this particular resonance structure of a ketone versus this one. you're looking at the one on the left and saying that one has a pi star. You're looking at the one on the right and saying that one has an empty p orbital on the positively charged carbon. I'm saying it can't be that way because two resonance structures have to be the same molecule. And so actually the picture that I've drawn is what it looks like, though if you want to think of that as an empty p orbital on the carbon, you sort of can. Yep, other questions? Yes?
Since the alpha carbon is a single bond and it can rotate, does that mean all of those protons on the alpha carbon are having hyperconjugation with the empty pi star?
Yeah, the question is, since that C-C bond here between carbonyl carbon and alpha carbon can rotate, does that mean that each one of them is experiencing hyperconjugation, at least as long as it's aligned up with the pi star it is? Yep, and you'd expect that to change as rotation happens. For that reason, this is really getting ahead. We're going to see only protons that can line up with the pi star can be acidic, only alpha, but that's like a couple months away, so I'm punting on that one. Yes?
Does the inductive effect and hyperconjugation always agree with each other? And if not, which one would you expect us to prioritize?
Ooh, that's a good question. Do inductive effect and hyperconjugation always agree with each other? And if not, how can you tell? I don't know. Yes, for the most part, yes. Basically, for the way I've taught the class in the past, last time I taught it, I didn't talk a lot about hyperconjugation because I thought it was overcomplicated. But then, over the holidays, I saw a headline for a paper saying, alkyl groups are not really great inductive electron donors. The real reason really is hyperconjugation. So I continue to teach the old and possibly false method because it gets you the right answer and it's easier, while trying to tell you some of what they think is the truth. But we're always learning in science. Okay, others? Did I miss a hand up there? No, yes. Okay. Oh, no, you're just, sorry. Okay, good. All right, so what I want to do now is go back to the question we had last time. Is the Y group a good leaving group relative to what? And we're going to use that question to navigate mechanisms that carbonyl compounds can do, and then we're also going to use those mechanisms to piece together two characteristic carbonyl reactions that you will see again and again and again. So first, we're going to do carbonyl mechanisms. The first one that you've seen so far that we talked about last time is nucleophilic attack. That is, the nucleophile attacks the pi star, breaks the carbon-oxygen pi bond, and gives you what we called a tetrahedral intermediate. Okay, so that's nucleophilic attack. I'm going to have some more to say about that step and how reasonable it is. How strong of a nucleophile do you need to be to attack a carbon-oxygen pi star? But today, our focus is going to be on the question of how good is the leaving group and how good is how good of a leaving group is the Y group, okay? So that's the tetrahedral intermediate. Second mechanistic detail for for carbonyl compounds is what I'm going to call the fate of the tetrahedral intermediate. And this will depend entirely on the identity of the leaving group. So here is a tetrahedral intermediate, and recall that our question was, is Y a good leaving group? But I told you that the question about Y being a good leaving group was always going to be bracketed by the issue relative to what. And right now we're going to answer the what. Question I want you to be able to answer is that Y group a good leaving group relative to the negatively charged oxygen in the tetrahedral intermediate? And TI is our abbreviation for that tetrahedral intermediate. Why are we worrying about this? Well, the nucleophilic attack is an example of an addition reaction. What I want to introduce now is something that can happen to the tetrahedral intermediate, and that is an elimination reaction. So you've heard the term elimination reaction before. If you think back to 351, whether that was last semester or whether that was before your mission, you probably have some memory of the letters E1 and E2, right? Real briefly, an elimination reaction occurred when you had a leaving group. I'm going to say that the leaving group is on a carbon, which I'm going to call alpha, and then a proton, which on a carbon that I'm going to call beta. And a base would remove a proton in the E2 reaction, would remove a proton from the beta carbon. At the same time as electrons in that carbon-hydrogen bond would kick down to form a pi bond between beta and alpha carbons, at the same time as the leaving group would leave. And your product had a new carbon-carbon pi bond between alpha and beta carbons. That look vaguely familiar? Okay, the leaving group left, Br minus, and then the base picked up the proton. You might also remember the E1 reaction, which was slightly mechanistically different. In the E1 reaction, it turns out, for various reasons that we don't need to dig into today, the leaving group would leave first in a slow step to give you a carbocationic intermediate, and then a base would remove a proton, electrons would kick down, and you would again make a new carbon-carbon pi bond. Again, carbon-carbon pi bond between the alpha carbon that used to have the leaving group and the beta carbon that was the one adjacent to it. That's an E1 elimination reaction. Now, one variation of this, which you may or may not have talked about in 351, is called E1CB. In E1, the leaving group leaves first, and then the proton gets removed. CB stands for conjugate base. In E1CB, it turns out the base removes the beta proton first, and electrons go on to the beta carbon. The product of that is the conjugate base of your starting material, negative charge on the beta carbon, and in the second slow step, electrons kick down to form a new pi bond between alpha and beta carbons, and then the leaving group leaves. So this is another reactivity pattern that you haven't maybe seen before, but it fits into the story of elimination. The idea is if you have a leaving group and a negative charge on the adjacent carbon, we'll call that negative charge the kicker offer, is the technical term for it. And those electrons can kick down and form a pi bond, and the leaving group can leave. If you like orbitals, from an orbital perspective, what's happening here is the lone pair is dumping into the carbon leaving group sigma star, breaking that bond and forming a new pi bond. Okay? So based on that, I want you to look at the similarity between that E1CB reaction mechanism, especially this intermediate with the kicker offer and the leaving group, and compare that to the tetrahedral intermediate. If for a moment we say the carbon that bears the leaving group is alpha and then the carbonyl oxygen is beta, do you see the analogy? You got lone pairs on the carbonyl oxygen of the tetrahedral intermediate can kick down and the leaving group can leave. That's an elimination reaction. And that creates a new pi bond between the oxygen and the carbonyl carbon. The nucleophile is here, and the leaving group, the Y group, is here. Okay? So that's something that can happen. That's an elimination step that can happen to a tetrahedral intermediate. But we want to get a good feel for whether or not that happening is reasonable. And the key consideration in deciding whether or not that elimination step is reasonable will be, is Y a good leaving group relative to the kicker offer? Essentially, we're going to be asking about the equilibrium constant for this reaction, and we're going to be comparing the stability of the Y group versus the negatively charged oxygen that does the kicking offing, whatever. So let's just draw a few tetrahedral intermediates and consider the reasonability of that elimination step. So let's suppose the leaving group is Cl minus and the kicker offer is O minus. So we're asking, what is the reasonability, or how reasonable or how favorable do you think this step is? What you're going to compare is Cl minus versus OR minus. And if you don't have that intuition down yet, you can always draw the conjugate acid of the kicker offer and the conjugate acid of the leaving group, or kicker or kickoff E or something. Look up its pKa, which is for HCl minus 7, and for the alcohol, the conjugate acid of the kicker offer is around 16. Which is more stable, the leaving group or the kicker offer? Leaving group, right? So you would predict that the equilibrium constant should be much greater than 1, that this is totally reasonable. You would predict that the leaving group is more stable than the tetrahedral intermediate. So yeah, you would predict that this is a totally reasonable reaction step, and you'd predict this to go in the forward direction. Does that make sense? Let's do another one. Let's switch to methoxy as a leaving group. Oh, sorry. What do you think about that one? You're not sure what to do there, are you? Because you see that the kicker offer and the leaving group are about the same in stability, right? They're both negatively charged oxygens. So you're not sure how to answer that in a multiple choice format, right? What if they're dead even? Do I say, yeah, it's reasonable? No, it's not reasonable. Let's ask in terms of equilibrium constant. Is this reaction more or less favorable than the one where chloro was the leaving group? It's definitely less favorable than that, right? Sorry, MEO minus is the conjugate base of an alcohol, methanol, which has a pKa of 16. It's not a very good leaving group, but that's why the question is always for us today, relative to what? Is it a good leaving group relative to a negatively charged oxygen? Well, I'd put the equilibrium constant somewhere around 1, meaning yes, it's reasonable, but it's not as favorable as this one. Does that make sense? So I'd predict this one to be pretty reversible. In fact, you would predict it to be pretty reasonable for actually the methoxy to come right back in and attack the pi star and form the tetrahedral intermediate again. We're going to have that consideration all the time as we go through mechanisms of carbonyl compounds. Is it okay for that leaving group to leave? Would it be okay for that leaving group, having left, to come back in and attack again and go backwards? This is how you make that judgment, is by comparing the stability of the kicker offer to the stability of the leaving group. So I would say this step here is totally reasonable from a mechanistic point of view. It's totally reasonable for lone pairs on an oxygen to kick down and kick off a negatively charged oxygen leaving group. Do I predict the equilibrium constant of that step to be very favorable in the forward direction? Probably not. And if I wanted to do this reaction in the lab and make it really work, there might be some other things I'd have to do to help move the reaction forward. Okay? Yes?
How much of a pK difference would you need to say it's reasonable but not much?
Good question. You want to pin me down on that? What pK difference do you want so that it's reasonable but not reversible? I don't have a hard and fast rule on that. You'll develop that kind of intuition just by experience. And though knowing whether steps are reversible or not is useful, I've never taken off points for a mechanism question where you failed to show an arrow that was reversible. So, all right. Go ahead.
For the top one with the chlorine, if the nucleophile was strong enough, couldn't it just do a substitution to get the same product?
If the nucleophile were strong enough, could you just do a substitution? At what stage?
Well, just like instead of the lone pairs on the oxygen.
So are you asking this question? Are you asking, does a leaving group ever do this? Or sorry, does a nucleophile ever do this? The answer is no. This is an important question. Does the nucleophile ever attack at the carbon and the leaving group leaves directly? No, because the lowest energy orbital, the lowest energy place for the nucleophile to put its electrons is always the pi star.
Okay, and that determines position.
And that determines where you're going to go. If you attack the pi star, you have to do that. The point is the pi star is going to be lower in energy than the antibonding orbital between carbon and the leaving group. That's an important thing. You will never see carbonyl chemistry happen with a nucleophile attacking directly and the leaving group leaves. You will sometimes see in biochemistry texts people showing arrows like that, but what they mean is they don't want to take the time to draw the tetrahedral intermediate and they're assuming that you can figure it out. I want to real quickly show you an example that would not be reasonable, where the reaction would be unfavorable for the leaving group to leave. So let's change that Y group. Instead of being methoxy, let's change the Y group to be a hydrogen. Okay? Asking the question, is it reasonable for electrons on the kicker offer to kick down and kick off H minus as a leaving group? And the answer is no, never, worlds without end. H minus is a terrible, horrible, no good leaving group. So you would predict that this equilibrium constant would be way, I need 1 billion arrows, less than 1. Unreasonable, unfavorable. And the reason for that is H minus is a terrible leaving group relative to negatively charged oxygen. Now, here's the fun thing. Nature can actually do this, but it never allows hydride to just go off into wherever as a leaving group. It has to have something in place to catch H minus right away so that it never feels like H minus. You guys heard of NADH before, NAD+? NAD+ is the thing that catches the hydrides. And so that's the only way this reaction works. Nature's figured out a way to do it that we couldn't do in the lab. Okay, with that, get going on Study Guide 13, and I will see you on Monday.